So in this class, we will discuss working operation of SCRs which are connected in series and also which are connected in parallel. First of all, we will recollect what is the need of combination of SCRs in power electronics. What is the need of combination of SCRs in power electronics, which we already discussed. Just we will recollect all the topics. Then we will go for the working operation of series connected SCRs and then parallel operation of SCRs. So need of parallel combination or series combination in power electronics. Only thing is to reach our required ratings. To reach our required rating. Required ratings means in terms of voltage ratings or in terms of current ratings. Our intention is to meet our required ratings. That is, required rating is nothing but voltage ratings or current ratings. For example, if you required a voltage rating, for example, if you consider a 10 kilovolt SCR, 10 kilovolt SCR, for simple understanding, if you consider 10 volts, a 10 volts SCR is considering, and these 10 SCRs can be combined in series. 10 SCRs can be combined in series to reach our required voltage rating. To reach our required voltage rating, because in series connection, all the SCRs voltages will be adding. That means if you are connected in proper way, then the voltage across each SCR will be in summation. If you, for example, if you consider 10 volts SCRs, if you are connected in 10 SCRs in series connection, then we will get almost 100 volts of rating. The combined series connection will produce a capability of 100 volts rating. That means to reach our required voltage rating, we need to connect all the SCRs in series. Similarly, if you require a current rating, high current rating, if you need a high current demand, then we can connect all the SCRs in parallel connection. All the SCRs in parallel connection. Parallel connection. So this is a requirement of parallel connection. For demanding high current, we need a parallel connection of SCRs. So this is nothing but the combination of SCRs. So in combination of SCRs, if you combine a series connection of SCRs are combinedly called as string. Series connection of SCRs or parallel connection of SCRs. Series connection of SCRs or we can say parallel connection of SCRs are combinedly called as string. That is, entire set is nothing but a string. So string is nothing but the combination of all the SCRs, whether it may be a series or it may be a parallel or the combination. Both, in some cases we need both. We need to meet the desired requirement of both voltage and current rating. In that cases we need series and parallel combination both. Where it can be useful means the combination of SCRs is mainly preferable when there is a HVDC transmission. When there is a HVDC transmission, high voltage DC transmission. In that purpose, we need a combination of SCRs to meet high voltage and high currents. For that purpose, we need a combination of SCRs. So this is a major application of combination of SCRs. Now we will see one by one what is a string efficiency. This is the points which we already discussed. Just now introduction part we covered. To meet high voltage demand, we need a series connection. To meet parallel, that is a parallel connection is required for meeting the high current demand. Okay. So what about the string efficiency? String efficiency is nothing but the measure of utilization of SCRs. String efficiency is used to measure the utilization of SCRs, whether you are utilizing all the SCR ratings effectively or not. That measure will be done by using a parameter, string efficiency. String efficiency is used to measure the efficiency, that is a utilization of SCRs can be easily measured by using a string efficiency. If you see the formula for that, string efficiency is nothing but the numerator part, there is a total voltage rating or current rating across the whole string. Total voltage rating in connection of series, or if you are connected in parallel, that is a voltage current rating. So total current rating or voltage rating of the whole string, complete string, divided by number of SCRs connected in a string, how many number of SCRs you are using to form that particular string, into current rating or voltage rating of each SCR. Current rating or voltage rating of each SCR. That is the formula for string efficiency. So if you see, if you are using equal equal voltage rating SCRs, if we use equal voltage rating SCRs, for example, in this previous case, we taken an example. If you are considering 10 volts SCRs, and we are considering that which are connected in parallel, or if you, for example, simplicity, if you are connecting 10 volt SCR rating is connected in series to meet a 100 volts requirement. To meet a 100 volts requirement, that means we need a 10 SCRs which are connected in series, each of 10 volts. Each of 10 volts. Like that, we are connecting a 10 SCR. That means we are trying to reach our requirement 100 volts. That is the thing. If for the same example which we discussed, if we calculate the string efficiency, what will be the string efficiency means for the same example which we consider 10 volts of each SCR, and we are using 10 SCRs to meet a 100 volts. That is for same example. If you apply a string efficiency, then it will becomes an 100% efficiency. String efficiency is 100%. That means we are utilizing all the ratings of, we are utilizing effective utilization of SCRs is created there. Effective utilization of SCR. That means we are efficiency is 100% means we are effectively utilizing ratings of SCRs. This is the ideal case. Why sir it is an ideal case means in practical case there is no 100% string efficiency. String efficiency is always less than 100%. Is always less than 100%. There is no 100% string efficiency will obtain in practical case. Why? Because SCR has different behavior. SCRs has different behaviors. If you see SCRs has different behaviors for the same rating, or you can say if a SCR is manufactured by the same company with the same rating, if you see the behavior or characteristic, or simply you can say static characteristics or VI characteristics of SCR, the SCR VI characteristics are different for same rating of SCR. That is a major problem. In practical case, if you see there is a difference in VI characteristics. So with that difference in VI characteristics, we are getting this type of problems. If you see the PPT, you can observe characteristics or properties of two SCRs of same make and rating, that is made by the same company and the same rating, are never same. Characteristics or properties, or you can say static VI characteristics. Static VI characteristics are behavior of an SCR of same rating and same making. Making is nothing but the same company and never be same. This is a major problem, and this problem leads to 5 major differences. This problem, due to the difference in VI characteristics, we cannot be comfortably connected in parallel, or we cannot be comfortably connected in series. Due to this practical problem, it cannot be comfortable. Directly we cannot connect in parallel, and directly we can connect in parallel because it damages the SCR overall. So what are the major problems due to this difference in VI characteristics means? First one is turn on time. There is a difference in turn on time due to the mismatching of properties. The second one is turn off time, and first one is turn on time. Both can be combinedly called as a dynamic characteristic. Dynamic characteristics are different. Dynamic characteristics, or you can say switching characteristics. Previously we discussed switching characteristics of SCRs are different. Two SCRs if you are selecting means two SCRs has different switching characteristics. That is a major part there. 1 and 2 combinedly called as a switching characteristics. And third one is leakage current in forward direction. There is a difference in leakage current in forward direction for both the SCRs. Similarly, there is a leakage current difference in reverse direction also. Forward blocking and forward conduction. In that case only we are getting leakage current. Forward blocking and reverse blocking modes, we are getting a leakage current. That leakage currents are different. What happens? The leakage currents are different means, if the leakage currents are different means we are getting different on-state voltages. Different on-state voltages, or you can say breakover voltage. Simply you can say, if you see the graph, you can clearly understand. If we have different leakage currents, this is the modified. Okay, this is the one which you can understand clearly. Just I am considering two SCRs. You see the VA characteristics. There is a different voltages. Here somewhat I modified. Practical case, there is no same leakage currents between two SCRs. There is no same leakage currents between two SCRs. So that is the thing. third and fourth point will make there is a difference in voltage ratings. There is a difference in on-state voltage rating. There is a difference in on-state voltage rating. And fifth one is recovery voltage. Recovery voltage is also differ. Recovery voltage is also differ. These are the mismatches due to the different properties of same making and rating of SCR. These are the mismatches. These are the different points, different mismatching points in the same making and rating of SCR. Same making and rating of SCR. So this is the drawback. Practical case, if you consider there is a difference in characteristics, that's why we are getting 5 different mismatches between two SCRs. If you compare with simply two SCRs, 5 different mismatching behaviors will occur. That is the first and second one is switching characteristics, and third and fourth one is being considered as a voltage difference. On-state voltage difference will be different for different SCRs. Different SCRs means in the sense different properties of SCRs. Whether it is a same making and rating, but it has different properties. With that difference, we are getting this problem. So these are the practical problems. If you are connecting directly SCRs in series and if you are connecting SCRs in parallel, these problems will practically occur. That's why we are not getting string efficiency 100%. That's why we are not getting string efficiency 100%. Why, sir, these problems will not affect on string efficiency? How can you say that? Means string efficiency is a ratio of voltages. We already seen previously. String efficiency is nothing but the numerator part. There is a voltage rating, total voltage across the string, and denominator if you see number of SCRs and also voltage of each SCR. That means there is a voltage rating will be there. Numerator is whole string voltage and denominator individual SCR voltages. If you have a practical problem, previously we discussed, due to the characteristic difference, we are getting different leakage currents and different switching characteristics. So with that problem, it will create a different voltage distribution. That means each SCR will not share equal voltages. Simple terms, if you say each SCR will not share equal voltages when you are combining in series. Previous case which we are considering as an example, each SCR has 10 volts and we are connecting 10 SCRs in series to reach our requirement of 100 volts. That is our concept. Ideal case we are assuming, but in practical case each SCR will not take 10 volts. It may take higher than 10 volts or it may take less than 10 volts, depending upon the characteristic behavior of the SCR. That is a problem with series connection. Due to that, we are getting unequal voltage distributions across the each SCR. Due to that, unequal voltage distributions occurred in each SCR. So with that problem, we are not getting string efficiency 100%. Not getting string efficiency 100%. So that is the reason why you are not getting 100% string efficiency in practical case. 100% means 1. Numerical value you can say 1. String efficiency never be 1. It always less than 1. String efficiency will always less than 1. Remember that string efficiency is used to measure the utilization of each SCR rating. Utilization of SCRs will be measured by using string efficiency. Utilization of SCRs is measured by using string efficiency. What about the reliability of the spring? Means reliability of the spring can also be measured with a separate parameter that is called as derating factor. Reliability of the entire string, not the device, reliability of the entire string can be measured by using a derating factor. Okay, derating factor. If you see the formula, derating factor DRF is nothing but 1 minus string efficiency. 1 minus string efficiency. Okay, that means in ideal case, if we consider string efficiency is 100%, ideal case means there is an equal voltage distribution. That is our assumption. Practically it is not done. For ideal case, string efficiency is 100%. That means string efficiency is 1. So for that case, string efficiency is 1 means DRF will be 0. Derating factor is 0. So for ideal case, string efficiency is 1, derating factor is 0. Whereas in practical case, string efficiency is less than 1. String efficiency is less than 1 because it will not crosses one value. It will not crosses 100%. That's why it is less than 1. Less than 1. So less than 1 means derating factor will be here also it will limit 1 minus, for example, string efficiency is 0.9. If you consider, for example, string efficiency is 0.9 for an practical string connected SCRs 0.9, then derating factor will be 1 minus 0.9. 1 minus 0.9 will be 0.1. So that is the difference. The remaining part, that is overall 90% is the string efficiency, means remaining 10% is the derating factor. In 100%, 90% is string efficiency, means remaining 10% is nothing but the derating factor. Derating factor is used to measure the reliability of the string. Derating factor is used to measure the reliability of the string. These are the basic concepts which we need to recollect before starting the working operation of SCR. So these are the problems which we already discussed. Due to the difference in properties and static behavior characteristics, we are getting mismatching in 5 parameters, that is turn on and turn off, and third one is leakage currents in forward direction and also in reverse direction, that is forward blocking and reverse blocking, and there is a difference in recovery voltage also. PIV, or you can say recovery voltage also PIV, or you can say recovery voltage. So there is a difference in PIV also. So these are the basic differences due to the difference in characteristics or properties of PSCR. So now we will move on to the working operation of series connected SCR. So we already know what is the problem while connecting the SCRs in series or in connected in parallel. There is a unequal voltage distribution. There is an unequal voltage distribution in each SCR. That is a major problem. That's unequal voltage distribution occurs due to the above reasons which we already discussed. 5 reasons we already discussed. So with that, we are getting unequal voltage distribution. So this is a major problem. So how to overcome this unequal voltage distribution? That means we need an equal voltage distribution. That is our requirement. But practically we are not getting an equal voltage distribution. So for that purpose, what we need to do to get an equal voltage distribution? So for that purpose, we are using a static equalization circuit. Static equalization circuit. See the circuit here. We can clearly understand what is static equalizing circuit. Here in this example, just we are discussing series connected SCRs only. So in series connected SCRs, if you see, all the SCRs are connected in series, and across each SCR we are connecting a resistance. So with that, so we are connecting an resistance. So that is nothing but a static equalizing resistance. You can say that resistance is nothing but a static equalizing resistance. Static equalizing resistance. So with that, we can get almost all equal voltage distribution across each SCR. Equal voltage distribution across each SCR, because if you see the diagram, all the SCR values are same. All the SCR values are same. So we are getting almost all equal voltage distribution across each SCR. Almost all equal voltage distribution across each SCR. So if you see the terms also, remaining terms what we mentioned in the diagram, there is a current I. I is nothing but string current, total string current. The combination current is I. And the next one is IBMN. IBMN is nothing but one SCR with leakage current, IBMN. Leakage current. IBMN is nothing but leakage current of SCR. IBMN is nothing but leakage current of SCR. Similarly, if you see n-1 SCRs, because already first SCR we already discussed, that's why remaining SCRs are n-1 SCRs. Remaining SCRs are n-1 SCRs with a leakage current of IBMH. That is, we can say simply IBMN is nothing but minimum leakage current, and remaining all the SCRs has maximum leakage current. That's why we are getting VBM is nothing but maximum voltage drop across resistance. So with this we can calculate the required resistance value, how much resistance we have to connect across each SCR. Here we have to understand one point clearly. for each SCR there is a different leakage current. That means for each SCR, we are connecting here n SCRs. That means each SCR has different properties. Each SCR has different leakage currents. So with that, if this SCR having minimum leakage current and remaining SCRs having maximum leakage current, that is our assumption. Practically, it may be different. Different means first SCR will have, for example, if you consider 1 amp of leakage current, first SCR, second SCR will maybe have 2 amps, and third SCR will maybe have 0.5. Like we have different leakage current. So if there is a difference in leakage currents, then the current passing through the resistance which are connected across each SCR will be different. Here in I1, I2, I1, I2, I3, I4, like that if you consider. That means I1, I2, I3 is nothing but the current passing through each SCR. The current passing through each SCR will be different because there is a difference in leakage current. But only one thing you have to remember is the voltage drop across each SCR will be varying, because voltage drop across each SCR is nothing but the voltage across each SCR. Each SCR means each resistance will have different current rating. So with that, we are getting different voltage distribution, but we are not getting any equal distributions here. But you said previously, sir, if we connected a resistance across each SCR, then we will get equal voltage distribution because we have equal resistance values across each SCR. That's why we are getting equal voltage distribution. But practical case, there is a difference in currents. I1, I2, I3, I4, there is a difference in current. This difference will occur due to the leakage current. That means here we have to think the resistance values will not be equal in practical. Each SCR has required separate rating of resistances. There will be not an equal resistance value. Then how can we get the equal voltage distributions? If we connect different SCRs, means we need to calculate R1, R2, R3 related to the corresponding leakage currents of each SCR. This is the practical case. For practical case, they are not calculating each and every resistance. If you are using 100 SCRs which are connected in series, means they are not calculate R1, R2 up to 100. They will consider only one thing, the optimum value of SCR, or you can say which value is opted for this 100 connected SCRs. Overall, combinedly in the sense, if you take, for example, 100 SCRs are connected. If you want for each SCRs, if you need 2 ohms or 5 ohms, like that, if you have, so from all the requirements, they are selecting an optimum value, which is very opted for all the SCRs. Reasonable value, you can say reasonable value of resistance, which suited for the present condition. So that particular optimum value will be selected. That optimum value, how you are selecting, sir? Not we are calculating each and every SCR. We are calculating used upon the voltage and current ratings of the SCRs. We are calculating based upon the current and voltage ratings of SCRs. How you are calculating means that is the formula which you are using here. We are represented here. That is R equal to N VBM minus VS by N minus 1 into delta IB. This is the optimum value. If you are selecting this resistance value, then all the SCRs will almost all share equal voltage value. Almost all, without any error, we can say we can get almost all equal resistance value. Remember, sting efficiency will not be 100% in practical. It may almost reach to 100%, not exactly 100%. So if you select this optimum resistance value, then we will get almost all nearly reaching to 100% sting efficiency. So what are the parameters here? N VBM minus VS by N minus 1 into delta IB. N VBM, N is nothing but number of SCRs in the string. VBM is nothing but voltage blocked by voltage. Read the sentences clearly. Voltage blocked by SCRs having minimum leakage current. Voltage blocked by SCRs having minimum leakage current. Because we are assuming that for calculation of R value, optimum value, we are assuming that first SCR will have a minimum leakage current and the remaining all N-1 SCRs will have the same leakage current of maximum value. That is our assumption. While calculating optimum value, we are thinking that first SCR will have a minimum leakage current. So with that, we are getting a minimum leakage voltage drop, VBM. So remaining all the SCRs, 100 SCRs means First SCR, we are assuming that there is a small leakage current, and remaining 99 SCRs will have maximum leakage current. That is our assumption for calculating the optimum value. It almost all suited the practical case. That's why we are selecting that one. So for that purpose, remember that VBM is nothing but voltage blocked by SCRs having minimum leakage current, and delta IB. Delta IB is nothing but difference between maximum and minimum leakage current flowing through SCRs. That is, delta IB is nothing but IBMN and IBMX. IBMX is maximum leakage current, IBMN is minimum leakage current. That difference we have to mention here, delta IB, and whereas VS is nothing but voltage across the string. Voltage across the string. So this is the thing, selection of optimum resistance value by using this formula. Okay, by using this formula. So this is the thing. One more drawback here is, one more drawback. What is the drawback here? For example, if SCR is in off state, that is, the switch is in off state. Switch is in off state means the resistance is continuously connected in the circuit itself, or you can say the string is continuously connected with the resistance. Even when SCR is in off state, the switch is in off state, the resistance is always connected in the string. That means there is a flow of, there is a possible of flow of current. There is a possible of flow of current in the entire string, even when SCRs are connected in series. So this is the drawback. So to eliminate the drawback, remember that the selection of R value, should be, because the current is already flowing in the string when the switch is off. So the resistance should be more. If you take more resistance value, then the additional current will be reduced. When the SCR is in off state, the current is flowing through the resistance. To avoid that additional flow of current, we need to select a resistance value which is actually mentioned here. Which is actually mentioned means N VBM minus VS by N minus 1 delta IB is nothing but the optimum resistance value. So exact optimum resistance value you should not select. You should select more than this optimum resistance value, slightly more than, not bigger value. So to avoid this type of problems while connecting in static equalization. Okay, so this is the thing in static equalization. And one more problem is also occurred. This is the problem due to the unequal voltage sharing. One more problem will occur because due to the 5 differences which we already discussed previously. Due to the unequal VA characteristics, we are getting 5 problems. Due to that 5 problems, we are getting 3 different problems. 3 different that is 3 different disadvantages, or you can say 3 different problems occurred while connecting in series connection or parallel connection. Due to the above 5 reasons which we already discussed, we are having 3 different difficulties while connecting in series and parallel. First one is unequal voltage distribution. Second one is temperature difference problem, which we discuss in the next class. Temperature, there is a possibility of temperature difference problem. And third one is nothing but the dynamic switching characteristics problem. That is turn on and turn off. Different turn on and turn off characteristics means there will be a problem with SCRs while connecting in parallel and series. So 3 problems will occur. These 3 problems will be discussed in the next class. Already we discussed the unequal voltage distribution today's class. In the next class we will discuss temperature difference and also the switching difference of SCRs while connecting in SCR. That remaining topic will be discussed in the next class. Okay, that is the thing for today's lecture.